you're ready to go. Enjoy.
Okay. Yeah. Well, it's my great pleasure to introduce Ryan Williams from MIT, who's done a lot of groundbreaking work, in particular on the interplay between algorithmic upper bounds and the implications for lower bounds, which I guess is what you'll tell us more about today. And also, quite surprisingly, the other way around, where he has used techniques for proving, in particular, low-depth circuit lower bounds to derive a lot of new algorithmic upper bounds. So yeah, it's my great pleasure to have Ryan give us a very interesting talk. So go ahead, Ryan.
Thank you, Casper. Good morning, everybody. So my goal in this talk is to tell you about a certain program for proving impossibility results in computing, which works by showing that other computing tasks are possible. So this is something we've been working on for some time. And my hope is that some parts of it excite you or inspire you to think more about it, or maybe they'll anger you so much that they'll inspire you to do something much better. It's probably the best case scenario for me. I'm going to assume very little background. There will be few technicalities and almost no proofs. One reason is that it's early in the morning for me, and another reason is that I'd be very happy if everyone were able to get something interesting from my talk. So here's an overview of the talk. I'll start with a very high-level view of conventional wisdom and where we depart from it. Then I'll discuss two different kinds of computational models, algorithms and Boolean circuit families, with the eventual goal of talking about limitations on circuit families by using algorithms for analyzing circuits, which is what I will discuss after that. And then I'll end with some details about how that is done, depending on how much time I have left. And I'll give an overview of the big picture. Okay, so we'll start with a view of TCS, at least in North America, how I see it, from 30,000 feet. There's sort of two kinds of researchers in TCS, roughly speaking. There are the algorithm designers, okay, and there are the complexity theorists. And the algorithm designers, they often ask these very positive questions. So what makes some problems easy to solve? How can we find a good algorithm for a problem? What does good mean? And by asking these questions deeply, we can find different definitions of notions of efficiency. We can find new kinds of ways of solving problems. Usually time is the resource we care about, but you can think about others. Now, complexity theorists, they ask kind of opposing type questions. So what makes other problems difficult? How can we prove that a problem is not easy? And slightly more technically, can we prove a lower bound on the resources needed to solve a problem? So can we prove a time lower bound or a space lower bound? And these kinds of lower bounds are, as you probably know, necessary steps for provably secure crypto. We need to have explicit, concrete problems that are difficult to solve with fixed resources. So the algorithm designer is asking for possibility results in computing, and the complexity theorist is asking for impossibility results at a really, really high level, okay? And so the tasks of the algorithm designer and the complexity theorists appear to be polar opposites. And algorithm designers prove upper bounds on the resources you need to solve a problem, and complexity theorists prove lower bounds, limitations. And so that's the conventional wisdom, okay? And it's generally believed that algorithm design is easier than lower bounds. So there are hundreds of algorithms papers published every year, and very few lower bound papers published. And so there's this conventional wisdom that they're doing opposite things, and the algorithm designers may have an easier life. At least it's easier for them to publish their papers. But no, they actually are proving more stuff. So in algorithm design, so again, conventional wisdom is that in algorithm design, you just have to find one clever algorithm for solving your pet problem. And once you've got that, you analyze that it works, and you unlock the secrets of this algorithm. Okay. Now in lower bounds, intuitively, you have to reason about all possible algorithms and argue that none of them work well. And somehow this universal quantifier over algorithms opposed to existential one seems to make the lower bound problem very hard. And I want to push back against this. I think this excuse is a bit misleading because there are thousands of worst case algorithms which actually analyze all possible finite objects of some kind. So, for example, there are like graph algorithms which do all sorts of magical things on all possible graphs, the overwhelming majority of which you will never see. So you can reason about all finite objects sometimes when we design a worst case algorithm to solve the problem on all possible objects. And so my opinion is that this kind of thing isn't why lower bounds are hard. In fact, there's more subtle reasons why lower bounds are hard for us to prove. Okay, so why are they hard to prove? So why can't we get started on proving things like P different from NP? So as far as we understand, like lower bounds, like strong lower bounds are out of reach for us at the moment. And the short answer is that there are many no-go theorems with various technical names, relativization, natural properties, algebraization. The high-level summary is that the common proof techniques that we use for proving lower bounds are not good enough to prove even weak lower bounds. So there are limitations on what these kinds of methods can do. So not only can we not prove this stuff like P different from NP, we can prove that we can't prove this stuff. Okay, and this is a depiction of me pointing one of my grad students like towards a lower bound problem. So there's been a lot of pessimism in complexity theory as a result. So I want to say a bit more about natural properties. But it's one of the many kinds of no-go theorems there are. But the natural proofs barrier, as it's often called, is something that I think cryptographers should know about. It directly relates to cryptography. So I will say a little bit more about that. So the setup is the following. If you're proving a lower bound against, say, restricted logical circuits, let's say you're looking at circuits that have log depths, there's only log number of layers of gates in them relative to the number of inputs. So let's say you're proving a lower bound and you construct a polynomial time algorithm, so an efficient algorithm that can distinguish most functions not computable with these circuits from all the easy functions that are computable with the circuit. So this algorithm takes in a truth table of a function, and it has to determine whether this function is one of the most functions, whether it's just some random function, or whether it's an easy function, something that actually has like a small efficient circuit family. And as my grad student, Raul Longo likes to put it, sometimes you can distinguish chaos from order. So you imagine a random function from a very orderly function, something with low circuit complexity. So then these logical circuits are too weak to support pseudorandom functions. So, okay, yeah, hi, Zvika. Okay. So then these logical circuits are too weak to support pseudorandom functions. So the polynomial time algorithm that you have can in fact distinguish PRF candidates from completely random functions. And so this is something that arises in the proofs of certain lower bounds. They kind of prove too much. They not only prove a lower bound, but they in fact like show that the circuit class can't support pseudorandom functions, which is actually believed to be true. So the moral is that if we believe it's possible to prove lower bounds, which are strong enough for crypto, then we must also believe that these natural proofs, these ways of proving things which are very constructive and have polynomial time algorithms embedded in them, can't establish results like P different from NP. And so the unfortunate part is that Razborov and Rudich showed that most existing arguments for strong circuit lower bounds can be naturalized. So they have a algorithm embedded in them somewhere. Okay, so I just thought I'd throw that in there as an aside, but it's something that I think should know. This is a significant barrier in proving lower bounds against circuits. So going back to the previous slide, so there are all these reasons that lower bounds are hard to prove, mainly because there are limitations of various proof methods. So how are we going to make progress? We have to find some way of looking at lower bound problems that don't relativize, don't algebraize, and don't naturalize. Okay, without going into what all that means, I'm going to talk about one way of doing that that I and my students and co-authors have been working on. Okay, and hopefully by the end of the talk, it will be maybe a natural way of looking at the problem. Okay, so we're going to be looking at connections between algorithm design and lower bounds, like unexpected connections. So I would say that they are much more than opposites. In fact, it might eventually be seen that the difference between algorithm design and lower bounds is more psychological than a logical one, in the sense that we'll talk about how algorithm design of various kinds turns out to imply lower bounds of other kinds. So the crazy thesis here is that designing algorithms in some sense is equivalent to proving lower bounds. So we're not going to talk about equivalences in this talk, but there are some equivalences that are known. I'm going to be talking about mainly the counterintuitive direction. So the counterintuitive direction would be algorithms imply lower bounds, because we were talking about the conventional wisdom is that algorithms are somehow easier to come by and lower bounds are difficult to find. So if you have an implication from here's an algorithm, it implies a lower bound, this is the unexpected direction for us. So at a really, really high level, we can see some sort of similarities, and we'll talk about this sort of matchup between the two in more detail. So a typical result in algorithm design has the form, here's an algorithm A, it solves the problem in all possible instances of the problem. So it's a worst case algorithm. It's solving the problem in all possible instances. You know, of course, I didn't say what the problem was and say what the instances are, but this is just the high level framework of what a result looks like, right? And a typical theorem from lower bound says, oh, here's a proof. I'm going to write down this proof that shows you the problem can't be solved by all possible algorithms of some type. So I'm going to rule out every possible algorithm for solving this problem. And so what we want to draw is some analogy between the algorithm in algorithm design and the proof in the lower bounds, and an analogy between the instances of the problem that we're solving in algorithm design and the algorithms we're proving lower bounds against. So the algorithms in the lower bounds that we're showing these algorithms cannot solve this problem. So this suggests that we should be looking at some kind of meta-algorithmic problem. So an algorithm that takes code as input. So if our instances are algorithms themselves, this is a kind of a problem where we take code as input and try to interpret or analyze the code and say something interesting about it. Okay, so this is the kind of problems we're going to be looking at. Okay, right. So here's like a high-level plan for possibly proving lower bounds in this way. So we want to prove results of the form. So task A is impossible for computation model B. Right. So what we're going to do is find results showing how algorithm design implies lower bounds. So we'll say if some task A prime is possible for computation model B, then task A is impossible for computation model B. So if we've got some A prime, it's possible in model B prime, we get that A is impossible in model B, right? And so then, you know, somehow we got this magic implication. We would use results from algorithm design to prove our hypothesis in this implication, that this A prime is possible in B prime. Okay, and of course, like the big question is, how on earth would we prove such an implication? And we're going to relate this A prime in B in A and B prime in some interesting way. So B and B prime will be different. So B prime will be like an algorithmic model, and B will be a circuit model. And A prime will be about circuits. It will be some problem that talks about analyzing circuits. And A will be some problem that is defined with respect to algorithms. Okay, but maybe, you know, this is like a bit confusing at 9 in the morning. So we could just think of it as a conservation of impossibility principle is what we're trying to prove. We're trying to say that at least one of these task A or A prime is impossible. Right? So either A prime is impossible for B prime, or A is impossible for B. Right? So you can think of it this way, and this can be a useful way of thinking about it. So there, at least one of these has to be impossible. Okay. So let me give like a simple example from complexity theory, and if the example is sort of, if you haven't seen this kind of stuff before, it doesn't really matter. Like the example, you could just tune out from the slide, and it will still make sense after that. But if you've seen some complexity stuff before, then this is some example to have in mind. So one example, it's like very simple example, is that if p space equals exponential time, then polynomial time is different from p space. So just to recall, p space are the problems solvable in polynomial space. P time are the problems solvable in polynomial time. X time is the problem solvable in exponential time. Okay. And the proof is very easy. So we say, look, if p time equaled p space and p space equaled exponential time, right? So if the opposite of the implication is true, then p time would equal exponential time. So we could take every exponential time algorithm and simulate in polynomial time. And this is impossible by the so-called time hierarchy theorem. So we can't just take arbitrary computations and just speed them up from exponential time to polynomial time, right? So this is saying like a certain algorithmic hypothesis implies a certain lower bound. And another way of saying is that like at least one of p space different from x time is true, or p time different from p space is true, right? At least one of these is impossible. So and many such results can be proved. Okay. Somebody might need to mute themselves. Unless you have a question. Okay. So many such results can be proved, but they don't seem very useful for proving lower bounds. And well, why is that? Well, I mean, these kinds of results, I like to say they're along the lines of, if pigs can fly, then pigs can oink, right? So we don't believe that p space equals exponential time. It would be like an unexpected, insane breakthrough. And we're saying in this implication, look, if pigs can fly, then something expected happens. Polynomial time is different from polynomial space. Yeah, I mean, we believe that's true. That must be true if p is different from np. So if pigs can fly, then pigs can oink. So these things are not useful. These kind of implications are not useful. We want implications with plausible hypotheses, things that are not only possibly true, but something we could probably prove in our lifetimes. So something maybe along the lines of, if cows can moo, then pigs can oink, or something. Perhaps a better analogy than animal stuff. But yeah, so this is an example, but it's not very good for the reasons I just described. We want some plausible algorithmic hypotheses that imply interesting lower bounds. Right? So okay, so getting that. So the big idea here is to look at two different models of computation: algorithms and circuit families. And so we're going to talk about how interesting circuit analysis algorithms can be used to prove limitations of circuits for modeling algorithms. Okay, so there are many open problems regarding how you can model algorithms with small circuit families. And recently we started to actually get a handle on them. They've been open for a very long time. So at a really big picture, so we imagine there exists some algorithm. So this is a Turing machine, my depiction of an algorithm. So a non-trivial circuit analysis algorithm. So what this is it is some Turing machine that takes all possible descriptions of a circuit, okay? And for every circuit that it receives encoded in, say, binary here on its tape, it can tell us, say, whether it's satisfiable, whether this is a trivial circuit that always outputs the same bit, for example. And let's say it's non-trivial algorithm in the sense that it beats brute force. It avoids trying all possible inputs to the circuit. Somehow it avoids this and decides satisfiability faster. Okay. So then, if we've got this kind of structure, there exists this Turing machine, so that for all circuits it solves SAT, we can turn this into a lower bound statement of the following kind. So we say there exists some interesting function defined with respect to Turing machines, okay? So that for all possible circuit families, if I take any finite slice of this function, so restrict it to some fixed number of inputs, then that slice cannot be computed by the circuits that I was able to analyze in my SAT algorithm. So as I can analyze more and more complicated circuits and solve the SAT problem for them faster than exhaustive search, I can find a limitation on circuits. I can find a interesting function that can't be computed by those circuits. And so I get circuit lower bounds. Again, this is a very, very high level big picture thing, and I will say more details about this as we go on. This is like really high level, and it will drill down more in a minute. Right, so how does this relate to our plan earlier? So our earlier plan for proving lower bounds. So our goal is to prove that some task A is impossible for efficient circuits. So this is going to be our model B. And what we're going to show is that non-trivial analysis of efficient circuits is possible with algorithms. So algorithms will be our like model B prime, a different model. And so we'll use this to show that task A is impossible for efficient circuits. So this is basically the implication I was alluding to on the previous slide. And then we just want to give faster circuit analysis algorithms. We want to give some faster SAT algorithm for various circuit classes and use this to prove that these circuits can't compute other kinds of functions. All right? Okay. So now I'm going to skip to this algorithms versus Boolean circuits, just give a big picture of the thing. I'm probably, for some of you, this will be a very easy review, but it doesn't hurt to think about this stuff again. So we've got two different models of computation here. We've got the algorithmic model, and it can take in arbitrary long inputs and still solve whatever problem we've got. And so this is computing some function from 0, 1 star to 0, 1. And in the circuit model, Boolean circuit model, right, we only take in fixed length inputs. Every fixed circuit only has a fixed number of inputs, and so it's computing some finite function. And we'd like to talk about what would it mean for a circuit to compute a function from 0, 1 star to 0, 1. So what would it mean for a circuit to be able to compute something that an algorithm can compute? There's an easy way to set this kind of thing up. We define a circuit family. So we just have an infinite sequence of circuits. So for every input length n, a circuit family has a circuit c sub n to be run on all inputs of length n. Right. So anytime an input comes in, you measure its input length and you feed it to the nth circuit in this infinite circuit family. Okay. So the notion of efficiency here, the notion of like an efficiently solved problem here is that of p poly. So these are the functions that are computable by a circuit family, where for all n, the size of c sub n is bounded from above by some fixed polynomial. Okay, so there's some, each circuit might be getting bigger and bigger. C sub 100 versus C sub 1000 might be blowing up. But they're only blowing up by a polynomial amount in the number of gates that they use. Okay. So this saying each circuit, is small relative to its number of inputs. Okay, there's still infinitely many of them. There's a different one for each input length, but there's a small number of gates. And so this circuit model, it has programs with infinite length descriptions. Okay, so this leads to all kinds of weird stuff. So you can get like undecidable problems in p poly by sort of encoding like an infinite language in a various way and in the description of your circuit family. In general, like if you've got like some program with infinite length description, the standard methods in computability theory are more or less powerless for trying to understand like what can't be done with such a computational model. Nevertheless, like circuit families are very useful. So why study this infinite model of computation? Well, for one, if you manage to prove a lower bound for this kind of thing, it's a very strong kind of lower bound. But so for one, like circuits could be easier to analyze in Turing machines. As far as we have found out, they're not. I mean, they could be easier to analyze than algorithms. So proving lower bounds for this, it could be easier based on maybe what kind of restrictions that we put on circuits. Another nice reason for looking at, say, p poly and trying to prove lower bounds for it, are that it's a step towards a non-asymptotic complexity theory. So non-asymptotic meaning there are no polynomials, no exponentials, just numbers, just concrete numerical limits on computing. So you could say in principle something like any logic circuit solving most instances of my 10 to the 3-bit problem needs at least, I don't know, 10 to the 125 bits to be described, to be written down. Okay, well, if you manage to prove this kind of trade-off between the input size and the size of the computation that you need, well, the universe, as far as we know, stores less than 10 to the 80 bits, is the so-called Bekenstein bound. And so this would be like some completely intractable problem for like a 1,000-bit instances. And such statements are really only possible when you begin to explicitly consider the trade-offs between the size of the inputs and the size of computations, which is what is happening when you study circuit families in p-poly and you're trying to prove a lower bound. You're trying to say that like for C sub 1,000, I'm going to require a circuit of some bigger than a polynomial in 1,000 type statement. And some of these kinds of non-asymptotic statements have been proved. So Meyer and Stockmeyer in the 70s proved such a result, but it was for some problem in exponential space. So it's like really, it's already like more or less intractable problem, and they managed to get a concrete limitation of this form for it. And getting this for a problem that we would, like something critical to a crypto system would be really nice to do. Okay, so this is a good motivation for looking at that instead of looking at, say, P versus NP, instead of looking at like polynomial time Turing machines, looking at circuits. Okay. Right, so how can we compare algorithms in circuit families? Well, so most Boolean functions require huge circuits. All right. So you might have seen this kind of result before, that if I take a uniformly randomly chosen function, Boolean function from n bits to a bit, it's going to need exponential size circuits. So if I just randomly toss a bunch of coins with really high probability, it cannot be compressed to a small circuit just by a counting argument. Just too many functions from n bits to a bit. So most functions will need exponential circuit complexity. Okay, and in fact, that lower bound is tight. You can in fact get for every function a circuit of size about 2 to the n over n. And so a very interesting question is, what natural functions require this kind of exponential behavior, this maximum circuit complexity? And the key obstacle is that non-uniformity can be very powerful. So we would like to be able to write down an explicit function and say, look, this one is among those many functions that required 2 to the n over n size circuits, but like we're extremely far from proving something like that. The main thing is that circuits can be extremely powerful because you get a separate one for each input length. You have this infinite computational model in principle. So a specific question we can look at about like this, which natural functions require exponential behavior, is we can say, what uniform algorithms can be simulated in p-poly? So by this I mean, like we have all these like big complexity classes. There's NP, but there's also p space, which contains NP. There's exponential time. There's even non-deterministic exponential time. Can these like huge uniform classes be simulated with small non-uniform classes like p-poly? So is it the case that if I take an exponential time computation, so some exponential time Turing machine, could I simulate it in p-poly? So is it the case that I can, for each input length, I can make a really small circuit that works exactly on those inputs, even though the Turing machine itself runs an exponential time? So this is in fact a largely open question, like whether or not you can compress uniform computation into so-called non-uniform, i.e. circuit complexity type question. So ridiculously open problem here is whether non-deterministic exponential time is in p-poly. So can all problems with exponentially long answers checkable in exponential time be solved with polynomial size circuit families? So the conjecture is that even NP is not in p-poly, but this is even harder than p different NP. So this is like some holy grail, very difficult question. But even knowing whether nx, the exponential time version of NP is in p-poly is open. Another kind of open question along these lines is, does every function in NP have a circuit family where every circuit has only linear size? So like some like 10n size circuit. So the best known is that, like, depending on what basis you use for your gates, it could be 5n or 3.01n. I mean, these are things that are still open. Like you could still compress computations down to linear size with circuits. But I would say that such problems seem easier then P different from NP, like NX NP poly and NP not in linear size. These problems seem easier for reasons that I'm about to describe. Like we actually have some way of reasoning about these questions, and we've been able to make progress by thinking in that way. The problems NX not in P poly and NP not in linear size are still open, but related questions around them have been resolved in this, using this way of thinking. All right, so let's move on to that. So how can circuit analysis algorithms imply circuit lower bounds? So let's define a canonical circuit analysis problem. So we'll look at what I call a generalized circuit satisfiability problem. The idea is you take some class of Boolean circuits, call it C. They could be Boolean formulas. They could be arbitrary circuits with like fan in 2 over AND and OR and XOR gates, however complicated you like. They could just be like 3 CNFs. They could be ANDs of ORs of at most 3 literals, as you would see like in the 3-set problem. So for every class of Boolean circuits that we have, C, there's a C-set problem where we're given a circuit K from this class. So it's maybe a formula or a 3 CNF. We want to know, is there an input to its variables that makes it print 1? And that's a satisfiability problem. It's a very simple circuit analysis problem from the point of view, we're just asking whether the circuit is trivial, whether it's the all zeros function, or whether at least one input makes it print 1. But of course, as you probably know, CSAT is NP complete for practically all interesting C. So it's very unlikely to be efficiently solvable unless P equals NP. Probably not happening. But we may still ask if there are ways to solve circuit SAT that run faster than the obvious brute force, which tries all 2 to the n input settings, the n inputs of the circuit. And so we can still ask this question, and it's a meaningful question. Like, could you solve it in 2 to the n divided by a polynomial time? And that there's nothing in the theory of NP completeness that rules that kind of thing out. All right, so it turns out that looking at that very innocuous question of like just improving slightly over 2 to the n is a key to proving circuit lower bounds. All right, so just the starting point for us was the following result. So this is a result of Karp, Lipton, and Meyer from 1980. So it says, suppose we had extremely efficient circuit SAT algorithms. Okay, then we can find problems solvable by algorithms in exponential time that don't have a polynomial size circuit family. Okay, so formally we're saying if P equals NP, so circuit SAT is NP, then exponential time is not NP poly. All right. So we're saying, okay, there are things that are solved in exponential time and they don't have a poly-size circuit family. All right. So this is an interesting implication, but it suffers from the same kind of problems that we saw before. We don't believe the hypothesis is true. So this is again of the form like if pigs can fly, if P equals NP, then pigs can oink. X is not in P poly. Yeah, we don't believe X is in P poly. In fact, we believe that X doesn't even have like slightly smaller than 2 to the n size circuits. So we would like a significantly weaker hypothesis than P equals NP and still be able to conclude a circuit lower bound from it. So I just wanted to point this out to let you know that people did have some connection in the past between algorithms and circuit lower bounds. Okay, so here's the kind of result that we have been proving. So we show that like slightly faster algorithms for circuit SAT, just things that slightly beat 2 to the n running time, would get lower bounds against circuits solving non-deterministic exponential time problems. And in fact, there's a trade-off. Like we now know that if your circuit SAT algorithm runs a little bit faster in exhaustive search, like as it runs a slightly faster, the complexity of your hard function goes from nx to something like non-deterministic quasi-polynomial, even down to MP, if your circuit SAT algorithm runs sort of fast enough. But even then, like the algorithmic hypotheses we're looking at are still within the realm of possibility. They're not like P equals NP type things. So there's some trade-off. And so it's in pictures, so look at this circuit here. It's got inputs, it's got some into the C size. Suppose we can inspect the circuit and find an input which makes the circuit print 1. And we do this not in to the n times into the c time, which would be the cost of exhaustively trying all possible inputs. But let's say we can do this in to the n over n to the 10 time. The 10 here is just a appropriately large constant. Okay, this something improving over exhaustive search by a polynomial factor. Okay, so even this kind of algorithmic improvement can imply a lower bound. So we can show for the same class of circuits, finite slices of nx functions cannot be computed by these circuits. So like if we were analyzing just arbitrary polynomial size circuits, we will have proved that nx is not in p-poly just by giving a slight break of the 2 to the n exhaustive search sat algorithm. So not even like improving like 1.9 to the n time, just dividing by a polynomial in the running time would already yield such a result. Okay, and there's a generic kind of statement we can make that will take circuit sat algorithms for various circuit classes and translate them into circuit lower bounds. So for example, we can show that, so this is what we saw on the previous slide. So, but if we could only solve the formula sat problem faster, I mean, this is quite natural to believe because formulas are very structured. They will look like trees when you write them as circuits. If you could solve the formula set problem faster than to the n, then you would get a lower bound against polynomial size formula families. So this is often called NC1, the class. But nevertheless, this is a big open problem to prove lower bounds against polynomial size formulas. And in general, for many different circuit classes C with various closure properties, if we can solve the SAT problem faster than to the n, then we get that nx is not in poly size C, okay, for different C's. But moreover, and this is a very intriguing result from the point of view of the algorithm design, we don't have to solve the SAT problem exactly. We don't have to solve an NP-complete problem. We can solve a problem that people believe can actually be solved in polynomial time deterministically. So here we're given a polynomial size circuit that's either unsat, so it has no satisfying assignments, or at least half of its assignments are satisfying. Okay, so it's like finding hay in a haystack type thing. So either there's no hay at all in the haystack, it's empty, or there's like hay, half of the assignments are satisfying. We want to distinguish between these two cases deterministically in faster than exhaustive search time. Okay, so this problem is easily solved with randomness. Just randomly sample assignments, and you can distinguish between the two. Do like a 10 random samples or something, and you have very high confidence that you will hit one of the pieces of hay in your haystack. Okay, but we want to do this deterministically. So it turns out that even solving this kind of de-randomization problem, so taking this problem easily solved with randomness and make it deterministic, would also imply all of the lower bounds we were talking about before. So if you could do this for Boolean formulas, you would get nx not in poly-size formulas. If you do it for circuits, you get nx not in p-poly. Okay, so really we don't have to solve the SAT problem. We can solve a problem that complexity theorists already believe could be solved in polynomial time. This kind of distinguish no satisfying assignment from many satisfying assignments. Okay, and so this implication was actually used to prove concrete lower bounds, which, if I have any time left, I would talk about. Actually, how much time do I have left? I don't remember when we started.
We started just a few minutes past 3, or yeah, I guess past your local time.
So
I would say you can go ahead for 15, 20 more minutes.
Oh, okay. All right. Okay. Thanks. Okay. Yeah. So this is one type of algorithms imply lower bound result we note, but the nx function, like nx, was like really complicated class. So the circuit lower bound looks pretty weak. It turns out that, well, I mean, if we were able to get slightly faster than to the n over polynomial running times, then we could get lower complexity functions, things much lower than nx. Okay, so just another set of trade-offs we can get. So here, isn't this talk 90 minutes, including questions? Your guess is as good as mine. I think I was told 45, to be perfectly honest. So, but I mean, yeah, it's fine. So 2 to the n divided by a sub-exponential. So 2 to the n divided by a sub-exponential, so 2 to the n to the epsilon for n inputs and 2 to the n to the epsilon gates. So this would be a better algorithmic result, right? So we're not dividing by a polynomial, we're dividing by like an exponential term, and we're not doing it for polynomial size gates, but exponential gates. If we can do that, okay, good. So then we would get a function that's not in, okay, just keep going. Yeah, all right. So so we wouldn't get like nx not in p poly, we would in fact get non-deterministic quasi-polynomial time is not in p poly. So we go from non-deterministic time 2 to the n to non-deterministic time into the polylog n. So this is a significant decrease in the time complexity of the hard function we're getting. And again, we get some generic implication between a faster circuit set algorithm and circuit lower bounds. Right, and even solving this problem, it's easily solved with randomness. You can call it gap sat, where it's either completely unsat or has many satisfying assignments. We would get these kinds of lower bounds. And indeed, we can get concrete lower bounds for this quasi-MP class using this kind of thing. And in fact, even if you got like 1.9 to the n time for circuit sat, or 1.9 in time for formula sat, then you would in fact get NP type lower bounds. So you get that NP is not in fixed polynomial size. So these connections even go down to NP functions, which is another thing that we approve. So this is work with my student Cody Murray. This MW is Murray Williams, 2018, and appearing in Fox this year, we have further improvements. So from circuit analysis algorithms, we can in fact get average case lower bounds. So we can show that there are functions in, for example, x to the NP that are very, very, very hard on average, like strongly average case hard, using circuit analysis algorithms. So there's been a lot of different directions in which this work has been pushed. I still think that we're just looking at like glimpses of something much bigger from different angles. So there's a lot, I think there's a lot more to be found. Maybe the next thing to talk about is why? Like, why would it be that getting a faster SAT algorithm would imply like a circuit lower bound? Why would it be that like just barely improving exhaustive search could even show something as strong as a long-standing, decades open circuit lower bound? So yeah, why are such implications true? And for y'all, I have some crypto intuition. So I had to say this crypto intuition is something that was a guiding principle for me, but none of my proofs of lower bounds look anything like this crypto intuition. Maybe one of you can make it formal. But nevertheless, I think it's a strong intuition. So if we have a faster circuit set algorithm, okay, this says it reveals a weakness of small circuits. So small circuits can't obfuscate the all zeros function as well as a black box could. So let's make this more formal. So I've got two different SAT algorithms here. Suppose on the left-hand side, I'm trying to solve black box SAT. So like my circuit is locked in a black box. Okay, I can't look at the insides. All I can do is query the circuit on various inputs and see the output. All right. And on the other side, I have circuit SAT. So I get the full circuit description and I get to analyze it and break apart the circuit however I like and study its insides. And under the hypothesis, I can solve circuit SAT in 2 to the n over n of 10 times. Okay, so I have a faster algorithm for that when you give me the circuit. So a very easy proposition is that, look, if I have an algorithm computing SAT on black boxes, so it only gets to query the black box and doesn't get to look inside the circuit, we can always find some box that will force our algorithm to call the box for about 2 to the n times. So it can just say 0, 0, 0, 0. Just keep making the algorithm query the box until the very end, and then maybe just randomly decide whether to print 1 or 0. And this is true even if we're promised that the black box is either completely unsatisfiable, has no satisfying assignments, or half of them are satisfiable. Like it will still take, there's still some box that will mess up this black box SAT algorithm. All right. Okay, so this thing will take at least to the end time, but if I've got the description, then somehow I can solve the problem faster. Okay, so this is somehow saying that small circuits can't obfuscate the all zeros function as well as a black box can. So a faster circuit SAT algorithm is just demonstrating some concrete difference between a white box circuit problem where I'm giving you the circuit and you get to analyze it and break it apart, and a black box problem where you don't get to look at the circuit, you only get to probe inputs and outputs, and you've got to decide the answer. So in general, there are other circuit analysis problems that I'm not going to talk about here that come up in this kind of work, and all of them have this sort of property that whenever I can solve one slightly faster, then I'm breaking like the difference between having the description and having a black box. And I think this is a good reason why you should expect a circuit lower bound. You're revealing some weakness of what circuits can do if you have a SAT algorithm for them. Okay, so that's crypto intuition that I like, although I'm not really sure how you prove stuff with it, but I like it. Okay, so there you go. Another intuition is that faster circuit SAT algorithms show a strength of algorithms running faster than to the end. So here we have some quicker algorithm that can tell when a given circuit computes all zeros, right? So we're showing, when we have a faster circuit SAT algorithm, we're showing two kinds of things. We're showing that like algorithms run faster than to the end are stronger than you think they can solve the SAT problem. And we're showing that small circuits are weak. They can't hide the all zeros function as well as the black box. So the idea, which I put in very small, tiny font because it's just intuition, is that we can construct some algorithmically defined function that doesn't have small circuits because we're showing algorithms are strong, circuits are weak. Okay, this is clearly hand wavy, but I hope you get some idea of why such implications might be true. Why would it be that the circuit SAT algorithm would help us prove a lower bound on SAT against some algorithmically defined function? Okay, all right, so let me now talk about some details, like how at a high level these things are really proved. Although I would love to see like any formalization of the crypto intuition. Okay, so here's one circuit lower bound proved in this way. This result that non-deterministic exponential time is not an ACC 0. Okay, so what is ACC 0? So I could go for a full definition, some polynomial size, constant depth circuits, yada, yada, yada. For y'all, I will just say, look, this is a simple but annoying circuit class. That's what ACC means, okay? Annoying circuit class to prove lower bounds for, proposed in 1986 by Barrington. It is the 0th such class. So basically, it is a class that almost certainly is very weak. It's polynomial size, constant number of layers of gates. Your gates are AND with unbounded fein-in or with unbounded fein-in, and you get to count up to some fixed integer. So that's mod m means you can count modulo m. So think of m as equal to 6. I mean, for the purpose of this, counting up to 6, mod 6 with some gates. These things are, there should be extremely limited. It's okay, ACC actually stands for alternating circuits with counters, but for us, annoying circuit class. Okay, it's super annoying, very hard to analyze. There was nothing known since 1986 about it, and then we finally got some non-trivial lower bound for it. Yeah, I think that's all we need to know about ACC. It's annoying. It was some significant barrier. So how was this thing proved? So it was proved by this kind of generic statements. If you take some typical circuit class like ACC 0, call this thing C, we had some generic connection that said if CSAT could be solved faster than to the end, then NX doesn't have polynomial size C circuits, right? This is the kind of connection we were describing before. And then we gave a concrete SAT algorithm for these annoying circuit class. So we showed that for 2 to the n epsilon size circuits for certain epsilons, you can solve the SAT problem in 2 to the n divided by 2 to the n epsilon time. So okay, so we're improving over exhaustive search. quite well for subexponential size circuits. And the key to this was it was just using a well-known representation of this class from due to Yao from 1990 that people long suspected should imply lower bounds, and we used it to get a SAT algorithm. Okay, and so this theorem B, right, it gives a much stronger algorithm than you need for theorem A. Like you're working with much larger sizes, and you're running faster. And this is exactly the starting point of much follow-up work. A lot of the follow-up work since in the last 10 years has been finding what are the implications of having such an algorithm? What are all the lower bound implications? It turns out there's quite a few. I won't talk much about this algorithm. I will talk more about how you prove this kind of connection, because it's a very generic thing. And I think like this is where maybe crypto intuition could be useful here, trying to prove how an algorithm implies a lower bound. So again, we have some circuit class C. We want to prove faster CSAT implies this kind of circuit lower bound. So the idea, the starting idea is quite simple. We just want to assume that non-deterministic exponential time has these small circuits, and we have a faster SAT algorithm. And we want to get a contradiction. Okay, so these are both positive assumptions, right? One is saying this huge complexity class has really small circuits, some positive thing, and we have a faster SAT algorithm for those circuits. So we're going to show that this, in fact, implies that non-deterministic time 2 to the n can be simulated in faster than 2 to the n time. So n time little o 2 to the n. And this contradicts the so-called non-deterministic time hierarchy theorem. And this says, like, as you strictly increase the time it takes to solve problems, there are strictly more problems you can solve. So we can't just generically speed up 2 to the n time in little o of 2 to the n time. Okay. Right, so this is what we want to do. This is the plan. All right, so we want to generically speed up 2 to the n time. How are we going to do that? So take any problem in non-deterministic 2 to the n time. How do we compute this problem? How do we decide it on an input? Well, there are two things we do in a non-deterministic algorithm, right? We guess a witness of order 2 to the n length in a non-deterministic problem, and then we verify the witness. We check the witness in order 2 to the n time. And so these are the two steps we do, right? And we want to speed up both of these steps, step 1 and step 2, using our assumptions 1 and 2. Okay, so we want to somehow speed up the guessing of the witnesses and speed up the checking of witnesses. And if we can do that in little o of 2 to the n time, then we're done. So that's what we want to do. So here's how we're going to. So given an input, we will compute the language, our given language on X by. So we'll use part 1, the assumption that NX has small circuits, to guess a witness of, in fact, polynomial size. So this is we can do this because of the so-called easy witness lemma by Impaliozzo, Kabitz, and Vigderson, which says that if NX was in P-poly, then every language in NX has small witnesses. So not only is there a small circuit computing the function, but for every verifier for that language, in every yes instance to that language, there are witnesses which have small circuits. The witnesses themselves can be encoded by small circuits. This is a very, very interesting structural result about consequences of small circuits. So this means that, in fact, we can guess witnesses encoded by small circuits in this easy witness lemma. But there are other ways to kind of get this thing if we don't have an easy witness lemma. So there are other ways to kind of get a small witness statement and other kinds of lower bounds. So that's how we reduce the guessing part. To reduce the checking part, we have like a circuit, a small circuit encoding a witness, okay? And we want to check that this small circuit encodes a witness fast. So then we can in fact use a faster CSAT algorithm to do that checking. And the really big picture idea is we guess our circuit encoding a small witness, and we have some big wrapper circuit around it that has copies of the circuit in it. And we set things up so that if this big overall circuit is unsatisfiable, then the original circuit inside encoding a witness is actual witness. And if it's so if it is satisfiable, then in fact this is not a good witness. So this uses a really highly structured NX complete problem. we can use PCPs to basically solve a weaker version of the SAT problem. We don't need PCPs if we just have a SAT algorithm, but we can use probabilistically checkable proofs if we just want to distinguish between unsat and mostly sat. This is a very technical bit, but it can be done, and there are various, we know multiple ways to do this kind of thing now. And so this is, so the SAT algorithm does the checking, and the circuit assumption does the guessing, and we get a faster algorithm this way. Okay. All right. So so I just going to conclude now. So over the last 10 years, we've managed to prove other connections of this form, quite a few, and subsequent lower bounds with co-authors and students. And I just want to say, like, getting more folks involved with a cryptographic mindset should lead to more progress. And as I've mentioned before, I don't know how to make my earlier crypto intuition formal. And so the main question I've been trying to address here is, how can we use our vast algorithmic knowledge to advance our understanding of limits? And it seems that there are ways we can do that via these SAT algorithms, but surely our vast cryptographic knowledge is also useful here. So I'll conclude by repeating something I've said many times in talks for other reasons, but I think it's important here for a different reason. So I think we'll only make serious progress by studying TCS as a whole, and not as competing subfields, not as having the algorithm designers over here, the complexity theorists over here, the cryptographers over here, and we'll only make serious progress by studying the connections between everything and studying it as a whole. Right? That's all I got. Thank you.
Maybe you can ask for questions if anyone has a question. Maybe, I don't know if you want to write in the comment section.
So I think most stuff.
Yes.
Yeah, go ahead.
Yes. First of all, thank you for allowing me to have this great opportunity. It is my distinct pleasure, Professor Ryan. So I have a very curious question here. Do you think that computational complexity theorists despise algorithm designers for their intent of doing what is practically useful?
No. I don't know. No, I don't think anyone despises anybody. I don't think. I mean, at least they don't ever say it to anyone's face, I guess. So, it's a pretty friendly field. No, yeah, even privately, I don't think. I think people, they just have different interests. I guess what I'm trying to encourage is sometimes your interests are served by looking just slightly beyond your immediate problem, the immediate problem set that you've been thinking about. Yeah, by reading things broadly and looking at things broadly. I remember whenever I first went to my first Fox conference, I was bewildered. Like, why are these people interested in this problem and this problem? This problem? It seemed so strange. Like, why were they looking at this? Why are they looking at that? I was missing context. I mean, every paper accepted to a stock Fox has an enormous amount of context, prior work, and and people were stumped at a certain bit, a certain thing they were missing. And it was because this new paper found that extra thing that made a difference. And so, yeah, I think like now when I go to StockFox, I don't have the same kind of experience. Like I can kind of see the bigger picture, and I understand a lot more context, and it makes a lot more sense. And this is from looking at things broadly. It's from looking at things broadly that this is possible. Yeah. Quantum, yes. Lower bounds and quantum complexity classes. Yes, this is a good question. I think in principle, this kind of connection should work for quantum circuits. I think it would need to be revised accordingly. But I do think that having algorithms for analyzing quantum circuits should imply quantum lower bounds against quantum circuits. If this is what, yeah, I mean, because this is also of obvious significance to cryptography. Yeah, I haven't personally worked out what those connections are. I mean, but I guess it's just low-hanging fruit at this point. They're trying to understand what hypotheses would imply quantum circuit lower bounds. But I see no reason why there wouldn't be some way to prove a similar connection. The connection is just that generic. Oh, there's another one. Faster set algorithms are easy if we allow randomized circuit set algorithms. Could give some intuition why randomized algorithms are not useful for lower bounds. That is, yeah, yeah. Why is that? I think I would say none of us really understand why randomized algorithms haven't been useful for proving lower bounds yet. And I think it will end up being just a gap in our knowledge that was filled by something else. It's a natural thing, Hotek, to say that if I have a randomized SAT algorithm, then I can prove lower bounds, not for non-deterministic exponential time, but Merlin-Arthur exponential time. Okay, it's a probabilistic version. But yeah, we don't have any way of proving that at the moment. Yeah, it is a bit funny how de-randomization in many cases turns out to be equivalent to circuit lower bounds. So there's a non-deterministic way of looking at de-randomization. It turns out to be equivalent to proving NX not in P poly. And yeah, so why wouldn't randomized algorithms give something? I don't know. Is your conclusion really matching the content of the talk results? Wait, which conclusion? That you completely separate the algorithmic task as needed from how you obtain the lower bound from it. So, right. Right. I put a lot of work into connecting two things so that people didn't have to look at the algorithmic task. But somebody has to look at the connections, right? And my hope is that cryptographers would look at the connections, and then you have to understand complexity and cryptography, maybe even algorithms too. But yeah, I think having these black box implications from algorithmic hypothesis imply lower bound, that's useful because a lot of people, yeah, maybe they don't want to think about lower bounds. They just want to talk about, oh, we probably can't do that because that would imply lower bounds or something. I think having those results those kind of statements is a very good thing, but somebody's got to prove them. Somebody's got to prove them. So we need people looking at all these things for somebody to prove the next one. So yeah, but other people might not have to if they don't, Does that answer your question? I'm not sure if I got the gist or not. Okay. Please explain why this general technique of implication of the existence of algorithm proves lower. It overcomes the barriers for proving P versus MP. Oh, so yeah, I'm not going to make a claim that getting a faster circuit set algorithm will help you improve P different from MP. So the barriers for proving P different from MP are, I think, much greater than what we're doing here. What we're looking at here are proving circuit lower bounds, but for non-deterministic classes that are bigger than MP, or the circuit, either the classes are bigger than MP or the circuits are weaker than P. So right, so these are weaker results than P different MP type things. But at a really high level, why is it getting around barriers? These barriers often talk about the genericity of arguments. So they just really briefly, these barriers say that, oh, your proof of like the time hierarchy theorem, your proof doesn't really look at the inside of the computation at all. It's like extremely generic, just uses universal simulation and so on. And so like it would work for lots of other models. And this is like the relativization barrier. So any kind of argument which is really generic and just looks at simulations at a high level won't work. But something which actually distinguishes between a black box and a description and is doing something significantly different on a description than a black box, if you start like making parts of the circuit black box, the SAT algorithm won't work at all. So So there's a certain sense in which having a faster SAT algorithm gets forces you to look more deeply at the circuit model than you would otherwise. And I mean, this is a high level reason why it gets around relativization. Another reason is that it is known that that within like the relativization, algebraization barrier, NX is contained in ACC, for example. Like there are oracles relative to which like these lower bounds are false. So we prove the lower bound, so we're getting around it that way. I hope that is some idea. So can the lower bounds for circuits have some practical implications? I would love to find practical implications. I don't know of any at the moment. Right now we're just trying to understand, what limitations we can prove and how. Maybe. So yeah, someone needs to look at it. I haven't really looked very closely at trying to get practical implications of it, but I'm not gonna rule it out. I've had a bet with Rod Fagan for maybe 20 years that P equals NP because he gave me 5-to-1 odds. What odds would you place in the conclusion that P equals NP? Good. No, this is not silly. So I was actually asked by some folks at Springer LNCS to write something. It's like the Springer LNCS 10,000 volume. They apparently have 10,000 volumes of these things. I was asked to like pontificate about the future of complexity, and so I wrote down some estimated likelihoods for various things, and I don't know if these are odds. I think I might have only given 85% likelihood that P different from MP, and I did that after Scott Aronson berated me for giving it 80% or something. I mean, I don't know. I would say that but like, how is the bet going to be settled? I guess like if someone actually proved it, like you should definitely be on the side that nobody proves it. Like you should get paid out if like nobody does anything, because that's what's going to happen. But in our lifetimes, like nobody, no, I would bet on like against it not being settled. Whether they're equal or not, this is different. So the bet expires this year. Oh, okay. All right. Well, I guess your money's safe as long as you don't pay out. Okay. Are potential scale downs conceivable? For instance, a certain algorithmic result saying NL is not in some block class. Perhaps. So the scale downs we've got so far are scaling down the amount of non-determinism. So we can scale down all the way to MP. To go down below that, I'm not sure. I don't know what sort of algorithmic hypothesis would imply that, but this is a very interesting question. Maybe first let's look at like what plausible algorithmic hypotheses imply exponential time circuit lower bounds. We actually don't have those. It's kind of funny because we have them for like quasi MP, but we don't have them for X. So that would be my starting point to try to like for looking at scale downs like this, go all the way up to exponential time and try to see what implies what implies it. Good. Yeah, I'm not really dogmatic about P different from MP. It's probably true. I mean, it's very likely to be true, I think, but yeah, I think at some point we have to profess our ignorance, right? Like we have to profess that, like there's some things we just don't know, and we don't even know how to get started proving. So, yeah, that okay. You asked, so there you go.
Okay, are there more questions for Ryan?
Otherwise, yeah, I guess I was just about to say maybe we should wrap up. Yeah. Thanks a lot, Ryan, for the very interesting talk.
Thanks for having me.
Actually,
Glad
there
you
is
enjoyed it.
Oh, there's an extra question.
yeah, there is last talk.
Recently, there have been results proving lower bounds for Boolean functions of approximate degree using upper bounds for certain quantum problems. Do I think the existence of some fast-solving quantum algorithms may imply circuit lower bounds? Yeah, this is right. So yes, I think so. Although I am not sure what lower bounds might get proved this way. So it would, like for example, if we look at things like Grover search, you can use these to show that there are functions in like quantum Merlin Arthur. You can show like better time space lower bounds for functions in quantum Merlin Arthur. This is some ongoing work with a student using Grover search. You know, whether they imply circuit lower bounds, I don't know, but the hard function would have to involve quantum. It would have to have quantum capabilities to be solved. But yeah, seems plausible.
Oh, more questions?
Might it be possible to prove that we cannot prove? It's possible, but we could probably. It's probably resolvable. I don't see any reason to think it's like continuum hypothesis or anything like that. I think it's just hard. This is really hard.
Okay. Well, thanks again, Ryan.
Yeah, thank you for the great talk.
Glad you liked it.